So thanks for the invitation. So I've been asked to give an overview talk on dark matter in astrophysics, and the previous talk has already nicely set up what I want to say. So I'm Aseem Paranjape. I'm from Ayuka. I don't work in particle physics. So I'm a cosmology, large-scale structure person, but it's very nice to be here at this meeting. So what I will try to do in this talk is address three basic questions. All related to this overall question of what do extragalactic observations say about the nature of dark matter. So the first topic I will talk about is how do astrophysical or baryonic feedback processes affect our inference on the nature of dark matter. Secondly, what are the predictions and limitations of simulations of both collisionless and non-collisionless dark matter models? And how do observational systematics and theoretical degeneracies impact the inference of the nature of dark matter? So the first two topics will be more or less an overview, and then this will transition into a little bit of the work that I am currently interested in. So just to set the stage, when you talk about dark matter in the astrophysical or cosmological context, a key theoretical prediction or key theoretical quantity is the linear power spectrum of total matter, which is dominated by dark matter. Right. And this is shown here. So what is shown is the power, that is the RMS fluctuations in the initial conditions of the dark matter density fluctuations that we think exist in the universe after inflation, shown in a dimensionless form as a function of wave number k. So towards the right, you have small length scales or large wave numbers. Towards the left, you have large length scales. Okay, so as you go here, you're reaching very, very long wavelengths, which probe the primordial power spectrum. And as you go to larger k values, you're probing smaller and smaller length scales. And the solid line shows you what you expect in a collisionless cold dark matter scenario. And these dashed and dotted lines show you what you expect in several cases of effective thermally produced warm dark matter particle as a function of the warm dark matter particle mass. So you can see that, if you have a 100 GeV kind of particle, then this kind of cutoff would happen way off to beyond the edge of the plot. But with keV scale particles, you might expect a cutoff here. What this is saying is that in the presence of this kind of effect, which is due to free streaming of these particles, you will not have any fluctuations at these length scales. And this is one of the key phenomenological probes that one wants to use in order to infer something about the nature of dark matter. This was also mentioned in the previous talk. And on the top, what has been done is to convert this wave number k into an effective mass scale, which tells you the kind of rough size of the region which collapses to give you perturbations at these scales. Okay, so these are very large masses, which are cosmological scales, like the entire universe. And these are very low masses and solar masses. We are reaching down all the way up to a few hundred solar masses and so on. So this is just to show you what the kind of theoretical picture is for the power spectrum of dark matter. Okay, so now the other thing that is important to understand when you want to try to connect to observations eventually is what you expect for gas and stars in our universe, because these are the things that we know they exist. Okay, so you have to understand how they evolve as a function of time. And to simplify things, let's just consider the case of collisionless cold dark matter. And it doesn't really matter which model of dark matter you use. More or less, the evolution of gas and stars is going to remain the same. So the idea here is there are tiny fluctuations in the dark matter density laid down by inflation. These evolve. We know how they evolve in the collisionless CDM case. You solve the collisionless Boltzmann equation. It is self-gravitating through the Poisson equation. This system is relatively simple to solve, at least on computers. And you will get, typically, I will show you more interesting plots rather than this cartoon, but bear with the cartoon for a time being. So these tiny fluctuations, they will grow into self-gravitating clumps of dark matter, which in the jargon we call halos of dark matter. Now the gas that is present in the universe will essentially follow it will respond to the presence of these deep gravitational potential wells. Because due to coupling between the photons and electrons all the way up to the last scattering epoch, the gas does not really gravitate until that time. It is a relativistic, effectively a relativistic fluid. But after last scattering, these potential wells exist already, and the gas starts condensing into these potential wells. And now if you just think about standard thermodynamics, as a gas condenses, it will heat up. But if you now just let this system go, at some point the gas will, it will stabilize because it is too hot to condense further. But this gas is made up of, elements like hydrogen, helium. These have atomic and molecular line transitions that are allowed. So at sufficiently high temperatures, these transitions will get excited, and electrons will go, for example, into excited states. When these electrons fall back into lower states, they will emit photons. These photons, if they are able to escape from the system, then they carry energy away from the system. Okay, so I have a clump of gas which has condensed and heated up, but it is now emitting photons, it is radiating. And if the radiation is allowed to go to large distances away from the clump, then the clump cools down. The fact that it cools down allows it to condense even further, because now pressure support has decreased and gravity can take over again. So this runaway kind of process, if it goes on long enough, can lead to clumps that are dense enough to form stars. And this is basically our understanding of star formation. This is the way I would understand star formation, not having come really from an astrophysics background. This is the way I understand it. Then there are many, many more details about how stars actually form. It is an entire research topic of its own. I will not go into it. Okay, so stars form, and then they conglomerate into these dark matter halos, and they form galaxies. Okay, collections of stars are galaxies. So basically our picture, cartoon picture, is that every halo may or may not have a galaxy in it. In some cases, you may not have had dense enough clumps forming. So those halos would not have any galaxies. They are shown as empty here. And in other cases, you would have galaxies. What we also know from simulations of dark matter is that these halos don't just exist on their own. They also gravitationally interact with each other, and they can eat up, a large halo can eat up other small halos and become bigger systems, which are kind of shown here. So these halos grow and merge with each other. And along the way, these galaxies go along for a ride, more or less. And as these halos merge, the galaxies also follow them along, and they become groups of galaxies. And our understanding of large-scale structure is currently built on this hierarchical picture, where I have small objects that form, grow, merge, and grow, and these galaxies which form out of this kind of process, and they also form groups. Okay, so this is more or less what we know about galaxy formation in the hierarchical paradigm. Finally, an extremely important thing to understand about our universe, because this affects a lot of things that we say about dark matter later, is the nature of astrophysical mechanisms that can inhibit this formation mechanism of stars. So I told you this basic picture in which gas cools, radiates, it heats up, radiates, cools, and then forms stars. But there are other processes that occur in nature which may inhibit star formation. So for example, we know that stars, when they grow old, they will become supernovae. And these supernovae, if they go off at sufficiently high rates and in tandem, they can drive winds of matter away from the place where they occur. Now, supernovae, of course, are individual stars which have gone off. So they're extremely small in length scale. But the winds that they drive, if several supernovae happen to go off together, the winds can reach hundreds of parsecs or even larger. Okay, they can reach kiloparsec scales. So they can reach galactic sizes, despite the fact that the individual supernovae are very small. So this kind of redistribution of material and of energy can in principle affect the formation of stars, because the redistribution of energy, as you might imagine, can heat up surrounding gas. And what I told you is that gas, if it wants to form stars, needs to be cool so that it can condense. Okay, so any mechanism that heats up gas has the potential to stop star formation. Also, if I have cold gas available, but because of a wind, this cold gas got driven away, or because of some other process like gravitational tidal effects or something, this cold gas gets driven away from the system, then I lose my fuel to form stars. Okay, so feedback processes can do two things. They can, or at least two things. They can heat things up, or they can move gas away, cold gas away, and both of these things will affect the formation of stars. So this is broadly what I mean by supernovae and stellar outflows, which can, for example, heat up material, or satellite-specific processes. So in this previous picture, when galaxies form groups, there is typically a big object in the middle, and then there are small objects moving around. These small objects are satellites of a central object here. So these satellites are moving in a gravitational potential of this object, and they are subjected to tidal forces. And these tidal forces can remove gas. Okay, so this removal of gas can happen because of this. And also reionization, for example, could lead to heating or ionization processes, which again suppress star formation. These typically happen at the low mass end, and they lead to this particular effect where if I take a dark matter only simulation and I ask what is the distribution of masses of halos, that is given by this solid line. This is a very well studied quantity. If I now say that all gas in the halos, so the gas to total mass ratio is known, it's omega b by omega matter. If all of this gas were able to form stars, then I would just take down this line by an amount which is multiplying every halo by FB, which is omega b by omega matter, and I would get a mass function for the galaxies that I expect. And what is shown here is the actual mass function of galaxies that you observe in nature. In large volume surveys, and clearly there is a large discrepancy here. So what I argued right now are effects, are mechanisms which can explain this large discrepancy at the low mass end because of stellar feedback. There is also a huge discrepancy at the high mass end. And for this one, there is relatively less observational footing, observational evidence. But what we believe happens here is that the fact that every galaxy is expected to have a supermassive black hole at its center, and the fact that these supermassive black holes are known in many systems to drive powerful jets of radiation of material out of the galaxy and out to megaparsec scales in some cases. So this has led to a conjecture long ago that maybe the fact that these jets exist and they drive this material out could influence the surroundings of these galaxies. And similar kinds of effects that you expect at small scales might now happen at very large scales, but now driven by these powerful jets. Okay, this is, at this level, it is a hand-waving argument. It really needs observational support. And as far as observations are concerned, there are right now, arguments both ways. But what is found, at least in simulations, is that without this kind of effect, you really cannot explain this large discrepancy at the high mass end. So you really need some powerful mechanism to suppress star formation in very massive objects. And the only thing that we can think of is the presence of this kind of AGN activity. So AGN stands for active galactic nucleus, which is the object at the center of a galaxy. So these simulations are cold dark matter, collisionless cold dark matter. Yes. I will show you some results. I may not show you the mass function, but I will discuss this as we go. Yes. What do you mean, what kind? This is the global stellar mass function. So this is over the entire gamma survey in this case. So this is not restricted to field galaxies. It includes at this end, it will include cluster BCGs. At this end, it will include field galaxies as well as satellites of clusters. Both will, everything is there. It's a cosmologically representative sample. No, don't worry about this. This is basically because these people wanted to show some extrapolations later on what happens. So there's observational uncertainty here about this end. So what they're basically saying is what is broadly the region that is allowed by the current observations. I should check. I don't think it is just survey incompleteness. There are other issues with, I suppose, with the stellar population synthesis modeling, etc. So I will check up on this later. Okay. So what this slide basically tells you how these problems have currently been resolved in hydrodynamical simulations of the universe. Okay, so these are state-of-the-art simulations run by the Illustris collaboration. So this is the Illustris TNG project. And there is a similar set of results also from the Eagle collaboration, okay, so which I'm not showing here. And basically what happens is that when you put in everything that you expect should occur involving stellar feedback and AGN feedback and allow for some freedom in the way these prescriptions are handled, you will get something that more or less reproduces the observations. Okay, so this has basically what has gone in is a considerable amount of modeling at what are called subgrid scales, because you cannot simulate individual supernova going off. Okay, so what you say instead is that I have a resolution element in the simulation, and what happens inside this element is determined by a set of equations. These equations are put in by hand, and they are differential equations that are solved with some free numbers. These decide how quickly stars form, how efficient the feedback mechanisms are, and so on and so forth. And these numbers are then adjusted so as to get the stellar mass function right. Okay, so that's the way things are done. Similar things are done with AGN feedback at the high mass end. With these kind of tools, what you see is that what was orders of magnitude uncertainty or orders of magnitude discrepancy between the expectation and the observation has now gone to factors of 2 discrepancies. And these factors of 2 are related to uncertainties in the way you model these subgrid astrophysical processes. Okay, so this is important to remember. This is state of the art, and these are the uncertainties that we live with now. Now, one interesting thing that happens is that the fact that this star formation efficiency is mass dependent, right? Because at the low mass end, I have a huge discrepancy. At the high mass end, I have a huge discrepancy. In the middle, I did not have a very large discrepancy. So I can say that the efficiency with which stars form, it decreases at the low mass end, it decreases at the high mass end, and it is at some maximum level in the intermediate mass. So this mass dependence has interesting consequences for things like the missing satellites problem and the void phenomenon, which we will see here. Okay, so basically what one says is, okay, now I don't want to have to run a state-of-the-art hydro simulation every time I want to say something about galaxies. So there are statistical ways of trying to address this issue. Basically what you say is that there is some physics which will take me from this dotted line to this observed stellar mass function. I don't know what this physics is. My simulation counterpart people have done a great job, and they have understood much of what is happening here. But what I will then say is that this has been solved, okay, by the simulators. So I will just make a statistical prescription in which I will do an abundance matching. I will say that I will take the number of objects that I get as a function of halo mass. I will simply match it to the number of objects, number of galaxies that I get as a function of stellar mass. And I will assume that the highest mass halos contain the highest stellar mass galaxies and go down like that. That is one way of doing it. There's another way of doing it, which says that I will statistically prescribe using some free functions. In a given halo, how many satellites do I expect? What should their luminosity be? What should the luminosity of the central galaxy of a halo be? And I will do this as a function of halo mass. So this leads to a couple of different statistical approaches, both of which have been remarkably successful. So this is this abundance matching approach where you just match numbers, and this halo occupation distribution approach where you make a statistical prescription. Both of these have been very successful in matching the stellar mass function or luminosity function by construction, as well as the 2-point correlation function measured in large scale structure. Okay, so this solves the problem for you in a statistical sense, not in a physical hydrodynamical sense. But having done this statistical solution, I can now start asking questions, because I can make mock catalogs, for example, or do analytical estimates of some other quantities. So the missing satellites problem, for example, says that in CDM simulations, there are many, many subhalos of 10 to the 8 solar masses in Milky Way sized halos. And also, correspondingly, if I look at voids, which are underdense regions, I expect many, many halos of the size 10 to the 9 to 10 to the 10 solar masses. So let's go out and look for the galaxies that live in these halos. Okay. Turns out the dwarf galaxies that should live in these halos are far fewer in number than you would expect just from a ratio of how many 10 to the 8 halos in Milky Way sized objects. Okay, there are several hundreds of thousands of Milky Way of subhalos expected in Milky Way size objects, but in our Milky Way, you see of the order of dozens or less than 100 satellites. So where are the corresponding dwarf galaxies? Or in statistical terms, if number counts of halo mass as a function of environment are large, then why are number counts as a function of light for a fixed environment small? Okay, and the answer, if you believe this mass-dependent star formation efficiency, is simply that this mass-to-light ratio, which I was showing in the earlier plots, right? The fact that there's a large discrepancy at both ends. There's mass in the dark matter and light in the galaxies. So the mass-to-light ratio becomes very large for these faint galaxies in any environment. So you make this hypothesis that this discrepancy between the halo mass function and the stellar mass function is independent of environment. If I make this simple assumption, it turns out that both the missing satellites problem in terms of number counts of Milky Way satellites as a function of stellar mass and the so-called void phenomenon, the apparent lack of dwarf galaxies and voids, both can be very nicely resolved. Okay, so these are not really problems once you buy that the fact that the star formation efficiency is a function of mass. Then there is something called the core versus cusp issue, which comes about in rotation curve fitting. So this is like change of gears. So when you fit the rotation curves of these dwarf galaxies, typically what you will say is that these are dark matter dominated systems. So I will just assume that the rotation curve comes from a NFW halo. I will try to fit it. And this is what you get. Okay, the NFW halo looks like this, and then the data looks like that. And then you say, oh, there is a problem. So I will look for alternative parameterizations, and then a model which seems to work very well. This is one example. There are other models which work well. Is where you introduce a core in the center of this halo where the dark matter density is not very steep. And then this seems to explain the data very well. And then you say that, okay, maybe there are cores in the centers of halos. So maybe dark matter is not collisionless, and maybe we are seeing effects of self-interactions, etc., etc. There was a very interesting study in 2017, and then another related thing in 2018, where these authors pointed out that even in simulations where I take NFW halos and I don't do anything to them, and I run simulations of full hydro, I create galaxies, and I observe these galaxies. So I project these galaxies into the sky. I put in these inclination effects and everything. And then I measure a rotation curve from these simulated galaxies, which have cuspy dark matter halos in them. Okay, and they're dwarf systems. What will I get? So what they said is, let's analyze these galaxies by assuming an NFW profile and by assuming a chord isothermal profile. And what you can see here is that the reduced chi-squared of your NFW fits are always substantially larger than the reduced chi-squared of your chord fits, even though the systems are cuspy dark matter halos. So they basically, they track down this problem to the fact that you are just assuming that the entire potential of the halo is given by the dark matter, and that there is no other force acting on the gas elements apart from the gravitational force. So both of these are problematic for these dwarf systems because there is pressure support in the inner parts of the halo, which can give, because of pressure gradients, it can give an additional acceleration, which was not modeled. And so when you account for these effects, you will basically recover your NFW fits, but without accounting for them, your NFW fits end up looking very bad. So whenever you see a fit to a dwarf galaxy rotation curve, which claims that it is discrepant with NFW, you have to ask this question, right? So this is one big caveat that comes in here. However, if you assume that these caveats are not there, if observation systematics are not an issue, and also if you assume that you know everything about star formation and feedback at these scales, which is again not really true, if all of these things are under control, then hydro simulations of CDM do seem to suggest that you should not have cores, and observations would then say that there is a discrepancy. Okay, so this is the level of caveats that one should remember. Sorry, how much time do I have? I'm basically out of time. Yeah, okay. Okay. So what I will do is I will complete the review part of my discussion, and then my own work, we can see if there are questions. Okay, so this was about astrophysical feedback processes. I want to say a little bit about simulations. I seem to have gone out of. Okay. I want to say a little bit about simulation techniques. So collisionless cold dark matter systems are extremely easy to solve these days because the underlying equations are very simple. Not to say that they are, not to trivialize the fact that these simulations can be run easily now. It has taken more than 2 decades of work to reach this stage where somebody like me can run an n-body simulation because the codes are publicly available and they have been well tested and so on. So what does one do? You want to solve the collisionless Boltzmann equation with cold initial conditions. This is not a tractable problem numerically because it is a very complicated phase space leading to a lot of multi-streaming, which is very difficult to track. So what one does instead is to approximate this system by sampling the initial phase space distribution function with the particles, because these particles are really phase space elements. And now to each phase space element, I give a position and a velocity consistent with initial conditions from cosmology, and I allow these particles, pseudo particles, to evolve. And then this is done using Newton's law plus the Poisson equation. Then I have to make sure that my particles don't undergo billiard ball collisions at small scales. So I will modify Newton's law a little bit at small scales by introducing a force softening or a core radius. This is completely numerical. So then at the end, I have to check that I'm not sensitive to this numerical artifact. And then you can improve the code efficiency, etc., by combining Fourier techniques with direct calculations. Okay, and then you can test for convergence of various statistics and so on. So there's a very nice review of these numerical techniques by Raul Angulo and Oliver Hahn that came out this year, which I encourage you to look at. So in this system, or in this way of doing things, what you can then do is, having run the simulation, you can go and try to find which regions of the simulation correspond to gravitationally bound clumps or halos. So you can identify these halos, you can identify substructure in them, you can construct merger trees and ask how these halos combine with each other and grew and so on. And simulation products include these halo and subhalo mass functions, accretion histories, the clustering of halos and dark matter, and all of this is very, very well studied. So this is in the realm of collisionless cold dark matter. If I now go beyond dark matter, let me look at one case study, which is warm dark matter. So warm dark matter is very nice because what has happened is that there was a dark matter particle which free streamed until pretty late. So it was relativistic until very late. But still, compared to the initial conditions of the simulation, which are typically set around redshift of 100 or redshift of 50, at these epochs, this dark matter is again basically collisionless. Okay, so what has happened is that the initial power spectrum has produced that cutoff, which I showed you in the first slide. But apart from that, the physics is exactly the same as a collisionless system. So all I have to do then is for these kind of cases where I'm talking about few keV or 10 keV or even 0.5 keV or something, I can ignore the thermal dispersion of velocities and treat these systems not only as collisionless, but also cold. Okay, effectively they are cold because their free streaming scale is so I don't have to worry about thermal dispersion effects. So now I can simply change the initial conditions of my simulation. My simulation code is a collisionless simulation code. I change the initial conditions by putting in this cutoff in the power spectrum, and I just run my n-body simulation. Okay. So this was a simple thing which people tried in 2001 or so. The problem is that there are numerical artifacts because in the actual initial conditions, there are no perturbations at small scales, but in the simulation, numerical artifacts will start gravitating. And this leads to this very interesting structure where, as a function of simulation resolution, you have these strings on a bead kind of structures that form. Okay, so these are spurious objects. They can screw up your counting of subhalos, and you have to account for them. So more or less, this is what one has to again remember. I think I am out of time, so I will maybe just leave you with this slide, which shows you the kind of structure that evolves in these alternate simulations. So here I've picked one warm dark. So these are two CDM simulations. This is a warm dark matter simulation. And this is what is called a ballistic dark matter simulation, which also falls into the same category. This was put forth by Basu and Rishi and their student. And again, it is a class of models where dark matter is essentially collisionless. So in these kind of models, you can now ask for what happens at small scales. These are the kind of features that, that appear. And maybe I will just go to my last slide, where I had a slide which showed. Okay, maybe I will just leave you with this slide on the Lyman-alpha forest, since people may be interested. So this is in the context of warm dark matter. So now with these simulations, along with hydrodynamics, people have been trying to place constraints on the warm dark matter particle mass. This is this paper by, latest one by Matteo Villa's group. And you can see that in the combined sample of these quasars, the green curve, this is the inverse mass of the dark matter. They've placed a constraint of about 5 keV at 95%. So I just wanted to leave you with the caveats that you should remember in this kind of analysis. They have tried to account for whatever I'm saying, but this is something that we are also now looking at. The main issue is that the cutoff in the power spectrum is degenerate with thermal effects in the intergalactic medium. So the intergalactic medium has a temperature, and the intergalactic medium also has pressure support. Both of these effects lead to similar kinds of cutoff in the power spectrum of the fluctuations in the Lyman-alpha forest. So what my student Bhaskar did here is to produce a power spectrum of the Lyman-alpha flux, of the Lyman-alpha forest flux, transmitted flux. And this is shown as the black solid line for a default model, which is in reasonable agreement with all observations. And then what he does is to just change the mean temperature of the IGM by moving it down by a factor of 5 in the blue and moving it up by a factor of 5 in the red. Okay, so more temperature means more smoothing, and the whole thing has come down. And with less temperature, it is less smoothing. Similarly, there is a gene smoothing scale due to pressure support in the model. And he's shown what happens if I increase the gene smoothing scale, I have more smoothing, or if I decrease the gene smoothing scale. So the point is, these kind of effects are very similar in even visually to these kind of cutoff effects. Okay, so when you want to constrain a cutoff, you have to account for these effects. Okay, so this is something we are now revisiting in the context of this, of some semi-analytical techniques, but this is something that one has to keep in mind. There are some other things also, but I think I've gone over the time, so I will stop here.
Nice overview on dark matter in astrophysics. Now we have time for questions, at least a few.
So I have a question regarding that cartoon that you showed, that you can have halos and then there are galaxy formations inside halos.
Mm-hmm.
Yeah. So you said like you can have galaxy-less dark matter halos as well.
In principle.
Then how do you experimentally observe them? If there are no galaxies or no stars inside those,
you will not observe them. Maybe they will affect lensing observations, but directly you will probably not observe.
But like theoretically, like their existence is like quite well.
This is the, I mean, if you like, this is the missing satellites problem, no? That there should be so many halos around, and you don't see them as galaxies. So I gave you an argument for why that might happen, because most of them might not have triggered star formation. Star formation efficiency is very low for low mass systems, independent of environment.
So towards the end, you talked about this ballistic dark matter scenario, and I think these dark matter becomes ballistic at certain time, right? And before
That's
that,
right.
it is
yes.
And if I understand, the effect of on CMB has been studied.
Correct. Exactly.
Does this have any effect on large scale structure? That
Thank you. Yes. So it's a very, it's like a what is it called? A planted question. So this is the thing I wanted to show. So this model that I picked was at the edge of being rejected by CMB. So it's consistent with CMB at 2 sigma. That's how we picked it. And then I ran simulations with it. I showed you those simulations earlier. And with the Shadab, what we were looking at is a new statistic called the Voronoi volume function. So what you say is that I have galaxies in a volume. I will tessellate this volume with Voronoi tessellation. using the galaxies as tracers. And I'll just record the volume of every Voronoi cell. And I'll create its distribution. And this distribution, we have seen it responds to halo properties. Okay, and now we said, let's do this in the CDM simulation and in these non-standard simulations and try to compare with data. So this is a crude comparison. The green shows you different percentiles of this distribution as a function of luminosity or as a function of halo mass, if you like. Okay, and it's parameterized by number density of the tracers. And in the various error bars and solid lines, I'm showing you these different simulations that I ran. So the point is that the CDM and WDM simulations, which is this cluster of lines here, they are more or less in agreement with these data. This is from the Gamma survey. But the BDM is this set of thin blue lines here. It is completely off. Okay, so this particular BDM model, which would be not very strongly rejected by CMB, is very strongly rejected by large-scale structure probes, which are sensitive to small-scale nonlinear dynamics. Because these Voronoi volumes, they can probe very small scales around the galaxies. So there is, in fact, this particular effect, which we have not managed to probe in greater detail than this because we are lacking. Oh, Voronoi volume is very simple. It is in 2D, it is very easy to understand. So I have some tracers. I have tracers. And I ask what is the volume around this point such that any point inside that volume, so let me just draw a toy volume. I want to see the points inside the volume. I want this point to be closest to this tracer than to any other tracer. So then I get a tessellation like that. And it is uniquely defined. Okay, so, and because in highly clustered regions, these Voronoi volumes will become very small. So these low percentiles, this is the 2.5 percentile, I think. This is 97.5. I think this is 2.5. Okay, so 2.5 percentile will probe very highly clustered regions where the volumes are very small. The 97.5 percentile will probe voids where the volumes, Voronoi volumes have become very large. I don't have many neighbors around me. Okay, so both of these in the BDM scenario are like completely off from the data. So this is something worth following up. Astrophysical solution, there is, yeah, okay, let me just see.
Can you repeat the question, please?
What was the astrophysical solution of the cusp core problem? It is not actually an astrophysical solution, it is an observational systematic answer to this problem. What they are saying is that I should not be doing the data analysis in this particular way, where I say that simply because I expect that the dark matter dominates in these systems, I will model a rotation curve assuming only the dark matter to define my gravitational potential. Okay, because if I do that, then I will naturally be led towards solutions which have a reduced chi-squared, which is low, assuming that the dark matter has a core, even when the actual dark matter does not have a core. So the reason was that, at least what they say, is that there is pressure support in these systems. So this pressure is giving you an additional force which is pushing the gas out, which is not
that pressure support coming from. I mean, is it a
this is pressure support
from formation or what?
It is, I think what they find in their simulations is that it is just the hydrodynamical pressure of the whatever gas is there, which has formed the galaxy. It may not be dominant over dark matter, but there is pressure in that gas, and that gas pressure is pushing the gas elements out. And that is sufficient enough in the inner parts of the halo to create this kind of spurious effect.
So this is free gas inside the halo, which is sort of pushing the dark matter out.
It is not dark matter. No, it is, see, the rotation curve comes from observing either stars or gas.
Yeah, that's true.
So it is the velocity of those gas
But
tracers.
the simulations tell you that there is a spike in the dark matter.
Correct, correct.
Which shouldn't. So what happens to the spike? How do you?
There is no problem with the spike. The dark matter can do whatever it wants. No, the gas will be supported anyway by its own pressure. Gas will not become.
Okay, so you're saying even if that spike is there, the gas has that.
Yeah. The gas has produced a nice realistic galaxy. That is the things that they observed. So
Let us take a few questions from the participants joining online. I can't see the name, so could you please ask your questions?
Okay, thank you again, Aseem, for this very nice talk. I think I will continue where the earlier question kind of stopped. So if I understood the early part of your review, neither the missing satellites nor the cusp core problem is something, I mean, both these things, the astrophysicists do think that they understand. I mean, and this does not, the conclusions that we are drawing about dark matter from these puzzles are most probably not necessary. Is that a correct conclusion?
I think this is correct at the present time. And the way forward, I think, is to do self-consistent simulations, which are now being done. Okay, so it's,
Okay.
with self-interacting dark matter, this is a particular issue, right? Because
Yeah, that's
dark matter
exactly
interact
what I
with
was leading
itself.
to.
Yes. So does dark matter interact with itself, or is it just the gravitational influence of baryons around it, which creates certain effects? Okay, because baryons definitely interact with themselves. So the way to do this is to do self-interacting dark matter models with hydrodynamics and put in feedback prescriptions, etc. Okay, allow for this freedom, astrophysical uncertainties, and then see what happens. So I think now there are a couple of groups which have started doing exactly these kind of simulations. But these are, I would say, in their infancy right now. I've seen papers in the last few years, but it will progress as time goes on.
Okay. Thank you.
Okay, last question from Deep Ghosh joining online.
So am I audible?
Yes.
So my question is regarding the free streaming, that that warm dark matter and cold dark matter can both that generate the dwarf galaxy of 10 kpc. So is there any astrophysical evidence, a single evidence, that would break the degeneracy between this warm and cold dark matter scenarios in future? Because both these models predict similar kind of free streaming as long as we are considering only the dwarf galaxies.
I think current constraints on warm dark matter are tightest from the Lyman-alpha forest, not from dwarf galaxies, because the dwarf galaxies have this additional issue of uncertainties in baryonic feedback, and you do not really know which galaxies should have turned on or turned off. But the Lyman-alpha forest is a study of the intergalactic medium at high redshifts, which probes early epoch of the universe when the density field was relatively milder. Okay, so we are not in the fully nonlinear regime. So it is a cleaner probe in that sense. That is what I was trying to show you here. So these are the constraints that come from the IG, the Lyman-alpha forest. And these constraints have these degeneracies, but you can account for them. Okay, so you can marginalize over these degeneracies to produce these particular limits.
Okay, very good. Let us thank the speaker once again.